Okay, so I was on part C of number 19. Okay, so we're just going to continue here. So I was using this equation here, and I got 10 is equal to my acceleration that I found in part B times time squared plus initial velocity times time. Now that looks like a hard equation to solve, and because it's got the t squared and the t there. So I'm going to do that by graphing. Okay, we talked about this way back when. There's a couple ways to do this. I'm going to go ahead and move this over to this side, get everything on one side of the equation. So I've got 1/2, you don't have to simplify, your calculator doesn't care, 0.42 x squared plus 5x, and then this is going to move over to here, so that'll be minus 10 now, right? So I've got everything on this side equal to 0 minus 10. And then since I have it equal to 0 here, means I can go ahead after I graph it and find the 0 of the graph. I don't know, here, let's just pretend that I had it in the regular window. So I'll go here and find second. Hold on a second. Yeah, that looks good. Sorry, just checking something there. I'm going to go second calculate and find the 0 of that graph. I have to do the left bound and the right bound here. It looks like it definitely happens between 0 and 10, so I'm not going to play the cursor game. I'm just going to type those in. 0, right bound is 10, and that crosses at time equal to 1.86 seconds. All right, fun stuff. All right, block pictured of mass 3.5 kilograms. It's pulled by a force of 7 newtons at an angle of 30 degrees. So let's see what we got here. We've got gravity would be 35 newtons, being pulled by a force of 7 newtons. That's the force of the pull at 30 degrees. I'm going to need to break that up. So let's see, that's going to be 3.5 newtons here. It's a 30-degree angle, right? The sine of 30 is 1/2. And then the cosine, make sure I'm in the right, not in the right mode. So that's adjacent, right? So that'd be 7 times the cosine of 30 degrees. And it's about 6.1 newtons. Now look, if this is 3.5 here, the normal force is not 35. If the normal force was 35, then I'd have a tug-of-war with 35 down, 35 up, and 3.5 up. That would mean the box would be floating up into the air, accelerating up, in fact, and that is just not happening. Now, I know the ups and downs are balanced because it's a box, right? And boxes don't float up into the air, at least not usually. So this is 35 down, this is 3.5 up, so this only has to be 31.5 newtons of normal force, so that the two ups balance the down. Okay? And, geez, lots of mistakes in this thing, huh? So I guess what I meant to say, looking at this, find the coefficient of friction. I think what I meant to say here, it's being pulled at a constant velocity. So listen, if you went this far and you just thought to yourself, well, what the heck, McGrath, what's going on here? And you weren't sure about this, if you think you know what to do with that now, then you should pause the video right now and proceed now knowing this. Okay, I suppose you're back now. I'll give you one more chance to pause. Okay, so if it's moving at a constant velocity, that means the forces are balanced, which would mean there would have to be this much friction. Right? It would have to match this. And you could do that if you wanted to. Right? We can't do the tick marks here because I've got one balancing out with two. One down and two ups. Okay, so find the normal force. We did that already. And then find the coefficient of friction. Well, I know that frictional force is equal to the coefficient of friction times the normal force. So the frictional force is 6.1 newtons. The normal force is 31.5 newtons. So means we've got a coefficient of friction of about 0.19. And remember, that is a unitless number, right? The newtons cancel out, just 0.19. All right, here we go, last problem. The block pictured of mass 23 kilograms is supported by a rope at a 25-degree incline. Draw a quantitative force diagram of the block. Well, let's just note here that it's not moving, right? It's suspended by the rope there, so, and this is frictionless. So let's see, that means the forces have to be balanced. So here's my gravitational force, 23 kilograms, so that's 230 newtons. And break that into components because it's on a ramp. And just remind you, we can turn that like that, right? So that's horizontal, and then we drop straight down and go straight over to this, right? That's where the 90-degree angle happens, right there. This is my 25 degrees, right there, okay? So that means my components, while I'm at it here, are 230 times the sine of 25 degrees. That's the opposite. And then 230 times the cosine of 25 degrees. That's about 208 newtons. Now, I know that it's not moving, right? The forces are balanced. So that means the normal force has to be also 208 newtons to balance that. And then it's not friction that's balancing this, it's the tension in the rope, right? That's got to be 97 newtons. So find the tension, well, we did that in the diagram, didn't we? So the force of tension is 97 newtons. If the rope is cut, what's the acceleration of the block? Well, if the rope was cut, then all of a sudden there would be no more rope, and then this would be the unbalanced force. The unbalanced force would be 97 newtons if there was no more rope to counteract it. So let's see, mass times acceleration would be equal to 97 newtons. The acceleration would be 97 divided by 23. I'm at 4.2. meters per second squared. And then, if the ramp's 2 meters long, how long does it take for the block to reach the bottom? So let's see, the ramp is 2 meters long, the acceleration is 4.2, and let's see, initial velocity would be 0, right, when we cut it. So there's my 3 things. And we want to know how long. So once again, it looks like we're going to use this equation, popular equation. So 2 plus 1/2 a t squared plus the initial velocity is 0, so that term goes away. And a little calculator magic. Looks like we want the square root of 4 over 4.2, or about 0.98 seconds, which is a little bit less time than it took you to do this review. So listen, just in parting words of encouragement, I think that you could expect the exam overall maybe not to be quite as difficult as this. This is a good sort of overview of everything that we did so far this semester, and I think you should certainly do your best to understand and master everything that's in this review. But we'll try to make the exam manageable, okay? Study, study.